Hi, I'm Professor Goins. In this video, I'm going to describe the integration technique where we will use the even-odd decomposition of a function. If you don't remember what the even-odd decomposition of a function was, watch my video that I posted describing that in the pre-calc library. I'll remind you what the even part is, but in that video I go a little bit more in depth on that idea. All right, so any function f of x, any possible function in real numbers to real numbers can be written as a decomposition, so a sum of an even function plus an odd function. And the even function we'll refer to as the even part, the odd function we will refer to as the odd part, and my notation, I use a subscript of e or an o. All right, so the other thing I want to remind you of is that if I take a look at an integral on a symmetric interval about the x-axis, so from minus a to a, over here from minus a to a. If I have an even function, in particular the even part, but this is true for, of course, any even function, if I integrate that, what I can do is I can double it from 0 to a. So I can go from 0 to a, of course this right here, double this is the same thing as that all taken together. On the other hand, if I have an odd function, then when I go from minus a to a, those two would exactly cancel out, and so I would always get 0 for any odd function on a symmetric interval about the origin, but in particular for the odd part of a function. And here's why that is going to be so useful in these examples. When I integrate any function, so let's say I was to integrate from minus a to a of f of x. Well, I can replace f with its even-odd decomposition. And then I can separate the integral. Since this is an odd function and it's a symmetric interval about the x-axis, that's guaranteed to be 0. And so this is just equal to the integral of the even part. And it turns out that there's a variety of functions where no other integration technique that you will see in your calculus class we'd be able to integrate by hand. You cannot do it. But it turns out that when I take away the odd part, it actually turns out to be pretty straightforward. So let's go ahead and I'm going to do 2 examples. The first example, we're just going to use a polynomial, so something that's really straightforward that this is not necessary to do, but it does kind of eliminate a little bit of the work. And then what we're going to do is show you another integral that no other integration technique would allow you to integrate it, but this will. So first example, let's say I was going to evaluate the integral from minus 1 to 1 of x to the third plus x squared minus 5x plus 4 dx. So we don't have to use the following because we can, each one of those is a power rule. It's not really that difficult to evaluate. But we can eliminate part of this because if you remember, and again, if you don't remember this, watch the other video, but the even part of this is x squared plus 4. The odd part is x cubed minus 5x. So the integral of those terms, since this is symmetric over the origin, if this was from -1 to 2, it doesn't work. But if that's symmetric, then this part right here we can simply ignore. And this would be the same thing as the integral from -1 to 1 of x squared plus 4. I could also, like I said, I could double it from 0 to 1. so it doesn't really matter. In fact, if I double this and I go from 0 to 1, then it's actually going to make my evaluation a little cleaner, because then I'm going to notice both of those are going to have a multiple of x, and when I plug 0 in, this is going to be 0. So let's do that. So let's make this twice the integral from 0 to 1 of x squared plus 4 dx, which would be x squared would give me x cubed over 3, so I've got 2x cubed over 3 plus 4x from 0 to 1. And then I plug 1 in, I get 2/3 plus 4 minus 0. And then that would give you, so 4 would be the same thing as 12 over 3, so that'd be 14/3. Right. So now let me show you the other example where the only way to do it is using the even-odd decomposition. Let's take a look at the following integral. We're going to look at the integral from minus 2 to 2 of x to the 4th divided by 3 to the x plus 1. By the way, I'd be curious if anybody out there has any other idea or has seen any other methods to compute this integral. Please leave it in the comments below. I've never seen any other way to do it other than what I'm just about to do. Okay, so I'm going to take this integrand and I'm going to find the even part of it. So let me remind you what the even part of a function is. The even part of a function is f of x plus f of negative x over 2. Okay, so for this function here, the even part is going to be, so it's x to the 4th over 3 to the x plus 1 plus f of negative x, so that would be negative x to the 4th over 3 to the negative x plus 1 all over 2. And let's see, so this is x to the 4th over 3 to the x plus 1 plus x to the 4th over 3 to the negative x plus 1. And since I'm dividing by 2, I could change that to multiplying by a half. So that means both of these denominators would have a factor of 2. And now let's, I want to combine those into a single fraction. So common denominator, we would need a 3 to the x plus 1. We need a 3 to the negative x plus 1. And then there's a 2. Okay, so then this first one here would give you an x to the 4th times that denominator, so 3 to the negative x plus 1, and then I'd have plus x to the 4th times 3 to the x 1. Of course, I can factor out an x to the 4th, so that would be x to the 4th. And I've got 3 to the negative x plus 3 to the x. Then I'd have 1 here and 1 here, so I'd have plus 2. And then down here, what I'm going to do is I'm going to FOIL that. So I'd have 2 times, so 3 to the x times 3 to the negative x would be 3 to the 0, which is 1. 3 to the x plus 1 would be 3 to the x. 1 times 3 to the negative x would be plus 3 to the negative x. 1 and 1 would give you a plus 1. And notice that the even part of this is x to the 4th over 2. Because that and that cancel. And that's super easy to integrate. So let's go ahead and do it. So therefore, the integral from minus 2 to 2 of x to the 4th over e to the, or I'm not, sorry, not e, 3 to the x plus 1 dx, so there's our original integral, is the same thing as the integral from minus 2 to 2 of x to the 4th over 2 dx. And rather than writing it up there, let's just squeeze it in down here. So that would give me an x to the 5th over 10 from minus 2 to 2. So that would be 2 to the 5th over 10 minus negative 2 to the 5th over 10. And 2 to the 8, 16, so that'd be 32. And I've got 2 of those, so that's 2 times 32 over 10. Sorry, this is getting squeezed in down here. So therefore, you would have 32 fifths. Got kind of messy as far as being cramped in the bottom here, so sorry about that. But the idea is that if I ever have a function that looks similar to this, and there's actually quite a few other examples as well. I'm just going to have time for one in this video. I can always do a follow-up video if people want me to, and show you some other variations where this method applies. But this, to integrate it, change it to its even part, and it turns into just a polynomial. So super useful. The only thing is, it has to be a symmetric interval. Again, if it's not a symmetric interval about the origin, then this method won't work.